Welcome to everyone, and welcome to this day 2 of Technical Agility Conference. We had a very good day yesterday. We had lots of learnings, 2 keynote speakers and the different track speakers. Lots of learnings and sharing happened. I hope that today also we are going to continue that journey. And today we have 2 keynote that is going to be today. One is just after, now it's going to start with Dave, and then Paul is going to be the next. After that, we will have the 3 different tracks, and each track will have 2 sessions. So be ready with your learning sessions where you want to go start and start understanding those sessions, right? One thing is, if you want to change the sessions between the tracks, there are ways like, okay, you can go to the top left of your side on this tool, schedule. If you will click, it will ask that are you going to get out of this session, and then you can just choose the new session from the agenda, right? That you can do at any point of time. Any point of time, if you have any questions, chats or whatever, right? So if you can use that questions to just write that your question for the speaker. At the end, when we will have some time, we will definitely utilize those timing for answering that question from the speakers, right? And yeah, of course, make it interactive. The moment you have some challenge or something that you want to understand more from the speaker side, you can just write those queries and questions. We will do that. Okay. So, okay, guys, I will not delay further. I'm having Dave Farley with me on this particular day to start with. And I know that you guys are already knowing him. But still, I have some privilege to just introduce him. So Dave Farley is a pioneer of continuous delivery. The moment you are hearing that word, probably you will get to know about him, right? So he's a thought leader and experienced expert practitioner in continuous delivery, DevOps, lots of software development practices like test-driven development and all, right, in general. He is also running his channel, which is quite informative sessions that he's putting there, right? That is something we can do. And nevertheless, I just wanted to emphasize one thing, like he has been a co-author of Jolt Award winning book, Continuous Delivery, which most of us might have read at some point of time, right? So that is very brief about Dave, though he is having a very extensive and rich background for, if I will start talking about that, it will take more time for that. So no further delay. And welcome, Dave. Welcome to this Technical Agility Conference 2020. And we are eager to hear you on your talk. So thank you. Yeah.
Thank you very much. Thank you for the lovely introduction. Hello, everybody. Welcome to my keynote. I want to talk today about software engineering. And during the course of my career, I've had 3 different phases, really, that I went through. In the early part of my career, I had job titles like software engineer or junior software engineer and that kind of thing. And then in the middle part of my career, I worked for organizations that really didn't like the term engineering. And we called ourselves software developers, or one place I worked, we had several grand wizards, I seem to remember. But we didn't really like the term engineer. And then in the latter part of my career, I got involved in building some seriously interesting and complicated software systems. And I think that what we started doing on those projects was a little bit more akin to engineering. And I started thinking differently about what that meant. And really, that's what my talk is about today. So I'm just going to share my screen now. So I hope that you can all see my screen. So I think that when we think about software engineering, the kind of thing that we think about is probably something like this. And this is not software engineering. This is to engineering, software engineering, what a soldering iron is to electrical engineering. It's a tool. It may be a useful tool, it may be a bad tool, but it's only a tool. This does not define engineering in any useful, workable sense. Often, one of the things that we think about is process, and we might think of a process like this. This is the diagram of the Scrum process, which is an effective agile project management process. But the Scrum process says nothing about engineering, really. The Scrum process mentions the terms code or software 0 times in its documentation. It's good for organizing people doing things. It's as good for plumbing as it is for software development. So this can't form the basis of an engineering discipline for us either. In more recent years, there's been the idea of software craftsmanship. So if you'll forgive me using the slightly sexist terms, craftsmanship, it's easier to say than craftspersonship. But when I say craftsmanship, I am meaning, for all genders. But when we talk about this, I think there are some good reasons why the craftsmanship movement began, the software craftsmanship movement began. And I think it's made some important contributions. But this too, kind of by definition, craftsmanship is not the same as engineering. Craftsmanship, it may form the basis of engineering practice, but it's not the same thing. So where is the software industry? What are the ideas? Well, I think that we are a craft-based industry at present. We are not doing mass production, and that's appropriate. I think that one of the big mistakes that we have made in the history of software development is to try and think of it in terms of producing things. If you think about production for a moment and the history of production, it's interesting. The vast majority of human experience has been involved in the production of physical things. And if we are producing something physical, if we're even something as simple as a pen or something like that, if we are producing something along these lines, then the design of this is certainly an interesting problem and maybe even a difficult problem to do it well. But it pales into insignificance compared to the problem of trying to scale up the manufacture of something like this. In order to be able to produce a pen at scale, to a price, to a quality, that's a very complicated problem. And so we have tended to become a little bit fixated with the ideas of the problems of production. Now, the difficulty when we start to apply that kind of thinking to software is that software doesn't really have a production problem. If we write some software, we can copy it millions of times for negligible or zero cost because we can just clone the bytes. So we don't have a production problem. Our problem is always one of design. It's always one of the problems of solving, understanding the problem and exploring the problem space to solve those problems. It's never a production problem in that sense. And so mass production techniques are a very poor fit, which kind of rules out techniques like waterfall and so on, for example, because those are the techniques of mass production. I think that where we are is that we are a craft-based industry at the moment. The quality of our output is variable. It's very dependent on the skills of individuals. We haven't found an effective way of amplifying those skills more reliably. And I think that's where we are at the moment. And when we made the step towards craftsmanship from trying to mistakenly apply the techniques of mass production, that was certainly a step forwards. But I think that where we should be is more along these lines. We should be starting to think about applying lean style of thinking and lean style production techniques to what it is that we are creating. The impact when we start applying this kind of engineering thinking in our discipline is profound. We see staggering numbers, often orders of magnitude improvements in quality and efficiency of the approach with which we can deliver software. The approaches that I think of as engineering processes genuinely create better software faster. And there's good evidence to back up those kinds of extravagant statements. The bottom line is kind of the bottom line. Organizations that practice these more, what I think of as engineering-focused disciplines, make more money than other organizations. So this is kind of important stuff. One of the things that's kind of interesting when we start talking about and thinking about engineering is for some weird reason, I tend to get involved in quite a lot of conversations about bridges. People say to me, yes, but Dave, software development is not bridge building. And, well, clearly not. It's not bridge building, of course. But then I think that bridge building isn't what we think of as bridge building either. If you're building the first kind of a bridge that's ever been developed before, that's a very, very different experience to building just another suspension bridge that's the same as every other suspension bridge that has been built for a couple of 100 years. They're very different experiences. If you're building let's say you're building a carbon fiber bridge across a vast span of ocean somewhere, that would be ridiculous engineering, where we'd need to be experimenting and trying new ideas out and trying to different materials and all of that kind of those kinds of ideas. And that's much closer to the kind of thinking that we're doing. So I want you to keep it fresh in your mind that we're not talking about, production engineering. We're talking about something else. So engineering is not really often what we think it is. And the other thing that's a characteristic of engineering is that it's different in different disciplines. Most disciplines, really, the term engineering just means the stuff that works as opposed to everything else. Chemical engineering is not the same as automotive engineering, which is not the same as aerospace engineering, and none of them are the same as electrical engineering or space engineering or bridge building or any of those things. Each engineering discipline has its own characteristics and some of its own approaches. There are some crossovers, some similarities, which we'll talk about, but each discipline is its own discipline. So one of the first things that we can think of if we're going to try and create a genuine engineering discipline for software is that it will be ours and it will be unique to us. It won't be a copy of somebody else's version of engineering. Engineering is also not the same at different scales. These two buildings are both engineered structures. The building on the left, if this was, a mass-produced shed from your local store, then it would have been engineered to a specific price point and a specific tolerance that would have been tried to design with using the minimum amount of material, so it could be built to a price and all of that kind of thing. But it's absolutely self-evident just from looking at these pictures that the level of engineering that went into and was applied to the shed on the left is of a different scale compared to the engineering that went into the world's tallest building on the right-hand side. If you're creating the tallest building in the world, then you're going to be pushing the boundaries of what's known. You're going to be experimenting. You're going to be doing computer simulations and building models and simulating earthquakes to represent the stability of the region, and so on and so on and so on. It's a very, very different thing. And when we look at physical things like buildings, it's absolutely obvious that the engineering in one is different in some way than the engineering in the other. And yet they will share some characteristics. They will be based on some scientific principles and using some maths to work some things out and so on. In software, it's not always quite so obvious that there are differences or that there should be. If I am writing software to sell books, should I be applying the same level of engineering discipline as if I'm writing software to monitor machines in a hospital that are keeping people alive? Is that the same kind of stuff, or is it different? Should we be applying different techniques? So Again, engineering is different at different scales, depending on the nature of the problem, and the scale of the problem depends on the rigor or the level of discipline that we need to apply. So also keep that in mind. I'm not saying all of these things you should be applying the deepest, most extreme form of engineering to simple software. But there ought to be some principles that are common. So let's look a little bit at some definitions. Here is a definition from Wikipedia about engineering, and it says engineering is the application of maths, empirical evidence, scientific and practical knowledge to solve problems. That's a useful starting point. I think maybe a better definition in terms of my purposes is this, which is my definition. Engineering is the application of an empirical scientific approach to finding efficient solutions to practical problems. And I've tried to be efficient with the words here, so I think all of those words kind of are meaningful in this definition. So we're going to be doing this within economical limits. So efficiency means economically efficient as well as the result that we create being efficient. But we're trying to apply, a rational approach to problem solving. I think if we start focusing on this, to my mind, engineering breaks down, software development breaks down really into two fundamental problems. We need, if we are going to treat the craftsman exploratory part of this seriously, then we need to optimize for learning. We need to become world-class at learning. On the other hand, which I'm going to talk less about today, there's another bunch of things we also need to optimize to manage complexities, compartmentalize complexity. And that brings in ideas like modularity, separation of concerns, cohesion, abstraction, loose coupling, and those sorts of things. But for the rest of my talk, I'm going to focus on these 5 things. These 5 things, I think, are the things that it would take us to get excellent world-class at learning and exploration. I can't imagine an engineering approach to software development that wasn't iterative, didn't employ feedback, didn't require us to build systems incrementally, and didn't fundamentally rest on being an experimental approach based on judgment from empirical evidence. So I want to go into each of these things in a little bit more detail. So we want to be iterative. Iteration is the act of repeating a process, blah-de-blah-de-blah. Oops, sorry, skipped too fast. It's the act of repeating a process either to generate an unbounded sequence of outcomes, not very interesting, or with the aim of approaching a desired goal or target or result. That's the bit that we're interested in terms of what we're talking about being iterative. Iteration is vitally important. It means that we can learn, we can react to what we learn, and we can adapt based on what it is that we've seen. It gives us those opportunities to learn. So it's kind of fundamental to our ability to do that. It allows us to steer towards a goal. We don't start off a project by knowing what the answer is. We start off the project usually by not knowing what the answer is and needing to refine and recalculate along our course. It allows us to adopt techniques like continual improvement. It allows us to refine our skills and abilities and techniques and processes and technologies to better and better fit the problem as we deepen our understanding of both the problem and our ability to solve it. It allows us to refine each of those things and improve them incrementally, bit by bit, until we get really, really good at something. You don't create a world-class team or a world-class system in one great leap. These are things that take time and refinement over time to get better and better. Next in my list of 5, feedback. Feedback is information about actions returned to the source of the actions. Feedback means that we can observe the impact of our choices and we can start to make more evidence-based decisions. It allows us to construct models like this. This is the model that I use often to describe continuous delivery. We're trying to optimize from idea to working software in the hands of users, and we're going to create executable specifications and use test-driven development and the feedback loops from those things to allow us to learn very, very quickly and efficiently, and so end up with a good result. We want to work incrementally, and there's a variety of takes on what incrementalism means. The way in which I mean it is in terms of incremental design. Evolutionary design, continuous design, evolutive design, or incremental design is directly related to any modular design application in which components can be freely substituted if someone improved and can ensure better performance. And so I want to describe this in terms of modular systems in a way that I hope might resonate with you. My wife says that I'm a serial nerd, but she's mistaken because I'm a parallel nerd, because I can be a nerd on multiple fronts at the same time. And so I'm going to demonstrate one of my nerdisms, which is about software development and engineering, and software engineering, with another, which is my interest in the space program. So this on the screen is a picture of the Saturn V. This is the spacecraft that took human beings to the moon and brought them safely back. This was a modular system, and that was a design decision that happened early on. Initially, that wasn't the idea that they had for how to build a system like this. So here are two coarse-grained modules of the system. The first part of the system, this part, is the Saturn V, and its job was to take the rest of the spacecraft from Earth into Earth orbit. The top part of the spacecraft is comprised of 4 subsystems. Here are 2 of them. This is the command module, and its job was to take astronauts essentially from Earth orbit to Earth. It was also their kind of their habitat. This is where they lived for most of the journey. But its principal job, the real design constraints, were around bringing the astronauts safely back from orbit to Earth. The second part of this is the service module. This is the bit of the spacecraft that was responsible for getting all of the spacecraft from Earth orbit to lunar orbit, and back from lunar orbit back to the Earth. And then there was a second couple of modules. These 2 modules were combined, called the LEM, the Lunar Excursion Module, and this was designed to land on the moon, land 2 astronauts standing up because they couldn't afford the weight of seats onto the surface of the moon. The top part is the Lunar Ascent Module, and that took the astronauts from the surface of the moon back up to lunar orbit so that they could rendezvous with the command module and service module and head home. And the bottom part is the Lunar Descent Module, and its job was to take the ascent module and the astronauts down to the surface of the moon from lunar orbit. Now, this wasn't the structure of the spacecraft that they had in mind when Kennedy said that they were going to go to the moon. What they had in mind was something more like a kid's space rocket, a sort of Wallace and Gromit space rocket that took off from the Earth, flew to the moon, landed on the moon, took off from the moon and flew back to Earth. That's enormously inefficient in terms of energy. It's also not very flexible. One of the attributes of modular systems is that they can be developed more independently of one another. In this case, the various parts that I've shown you were built by different companies, different organizations. The lunar module that on the screen now was built by one part of the aerospace industrial complex in the States, and the command module and service module by another, and the launch vehicle by yet another. So that gave an opportunity to kind of parallelize the development of these complicated systems and make progress. The other thing that you get is that you can compose the system in different ways if it's modular. And so when the Apollo 13 disaster happened and the service module exploded, the astronauts and the mission control specialists were able to reconfigure the spacecraft and use this part of the spacecraft essentially as a lifeboat and bring it all back to Earth and save the astronauts' lives as a result. So modular systems give us more opportunities to be more innovative and to work more in parallel. Now, I've just used two different words in my list of 5 that are very similar to one another. So it'd be good to disambiguate what we're talking about. And I've stolen this picture, which I love, from my friend Jeff Patton's book, the user story mapping, which he just makes it clearer than I've ever seen anybody make it. So this is what iteration is about. You start off with a rough sketch of what it is that you want, and then you fill in detail across the piece until you get to a point at which you're comfortable with it, and then you stop. Incremental is different. Incremental is about this modular thing. So you do some modular parts and you do that to completeness, then you do other modular parts and you assemble the picture, the whole system, from those modular parts. I think it's hard to imagine software development on any kind of scale that doesn't take both of these behaviors seriously and kind of put it at the heart of the software development. You don't build complicated systems in one great leap. You build them iteratively and incrementally, and you subdivide the problem into components that people can work on more independently of one another, and each of those components is iteratively evolved over time and refined to become better and better at the job that it's supposed to be performing. The next of my 5 is being experimental. An experiment is a procedure carried out to support, refute, or validate a hypothesis. Experiments provide insight into cause and effect by demonstrating what outcome occurs when a particular factor is manipulated. I'm going to tell you another space story to try and paint the picture of how important experimental approach is. In 1961, John F. Kennedy, the American president, stood up in Congress and made the famous speech that kind of gave NASA the impetus to go to the moon. He said, "I believe that this nation should commit itself to achieving the goal, blah, 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 of sending people to the moon and bringing them back safely." At that moment in history, this was 2 weeks after the first American had gone into space. The first American in space was unbelievably brave. His name was Alan B. Shepard, and he was strapped essentially inside a tin can on top of a intercontinental ballistic missile. He was launched just about 100 miles up and in a parabolic arc, and then he parachuted down again. He didn't go into orbit. At the time, the intercontinental ballistic missile that was sat on top of, they were exploding all of the time on launch because they hadn't got the engineering right for that yet. So because of the Cold War impetus, Alan Shepard strapped to the top and launched into space. 2 weeks later, Kennedy stood up in Congress saying, "We're going to the moon." You can just kind of imagine the reaction in NASA the next day because they had no clue how to do any of these things. So Kennedy's done what leaders do. He's kind of established a vision. He's presented a goal, a target, which the organization is meant to aim for. Somebody once said to me when I was presenting this bit of this story somewhere else, "Is this the most expensive user story of all time?" And I think it's got a shout. I think it's a good candidate for that. So Kennedy's come up with his user story. We're going to the moon and bringing people back. And he's done what politicians done. He says, "You're all engineers, you're smart, figure it out." That's not wrong. It's not his job to figure out how to do it. It's people like ours' job to figure out how to do those sorts of things. Now, the problem is, as I said, at this stage in history, NASA, nobody had any idea how to solve this problem. Here are a collection of pictures that just illustrate some of the problems that they hadn't solved yet. They hadn't got launches sorted out. On the whole, if you look at a montage of space rocket launches from the very late 50s and early 60s in America, you see lots of explosions, lots of things blowing up. They hadn't got multi-stage launches sorted. They hadn't got the splashdown phase sorted, the return of the astronauts. The next mission after Shepard's mission, which was Gus Grissom, they lost the spacecraft and Grissom nearly drowned. That they hadn't developed a spacesuit that would allow people to do a spacewalk. Nobody had done a spacewalk, Russians nor Americans. They hadn't got the control center sorted. The modularity that we talked about, none of this stuff, no two spacecraft from anywhere had docked in space yet. So where do you start on a problem of this scale? So one place where you start is that you start by hiring some extremely talented, skilled people. This is the first software engineer. This is Margaret Hamilton, who literally was the person that invented the term software engineer, because nobody up until that point in history had ever thought of this as being related to engineering. She was extremely smart. She was the leader of the flight control systems for the Apollo program and led a team at MIT that developed the software. It was her software and her team's software that saved the mission when people eventually did get to land on the moon. But what else do you do? I mean, we've got to try and solve this problem somewhere. And a key to engineering in any frame is to take small steps and carry out experiments. So here's a picture of the Earth-Moon system, except this isn't really a picture of the Earth-Moon system. This is a pretty kid's storybook kind of picture. Here's a more accurate picture of the Earth-Moon system. This is to scale, and at this point in human history, no human artifact had been more than 1 pixel on this picture away from the picture of the Earth. So, problem one, how do you get anything from all the way over there on the left-hand side to all the way over there on the right-hand side? That's a monumental problem. You can kind of imagine the engineers in NASA the day after Kennedy stood up and set them this goal. And by the end of the decade, we're going to send men to the moon and bring them back safely. You can imagine them sitting there saying, oh no, what are we going to do now? How are we going to do this? I haven't got a clue how to do this. How do we even start? Oh, I've got an idea. We could put some astronauts into a space rocket, send it off to the moon, and see if they come back. No, this isn't the right approach for waterfall. So let's try a different approach. How could we simplify the problem? How could we begin to learn enough to be able to do this? Wait, I've got a great idea. Why don't we send the spaceship to the moon and bring it back, but don't put any astronauts in it? Well, that's definitely an improvement. That definitely simplifies the problem. It means we've got less weight to send to the moon, and we're not going to kill people. So that's probably a good idea. What else could we do? Oh, I've got a really good idea. Why don't we build a space rocket and send it to the moon and land on the moon, but don't bring it back? That would nearly halve the problem. That is a great idea. That's fantastic. That would make it an awful lot simpler, the spacecraft that we first had to send to the moon. Okay, so what does landing on the moon mean? It doesn't have to survive the landing on the moon. And that was the goal of this program. This is the Ranger program. These were literally target practice for spaceships. This was spaceships as bullets to see if you could hit the moon. And the program was just that. That was the goal of the program. So how did that go? How did that work out? Well, the first one, remember what I said about not being very good at launching space rockets yet? It blew up on the pad. The next one, the target of these two missions wasn't to get to the moon, actually. It was just to get the spacecraft into Earth orbit, just to prove out the systems. The second one blew up on the pad as well. If you've ever worked in a big project, the next one will make you laugh, because they haven't been able to get the thing off the launch pad yet, but Ranger 3, they're going to go for the moon anyway, despite not having succeeded getting it into Earth orbit yet. So they went for the moon, and they did get it into Earth orbit. They managed to improve, and they shot it off towards the moon, or at least they shot it off into space, but it missed the moon. Ranger 4, it kind of worked. It got into Earth orbit, it did the deorbit burn, headed off for the moon. Almost immediately it left the Earth, all of the systems failed. But they managed to track it from ground-based stations, and they saw that it did actually hit the moon. So that's a huge step forward, and a lot of lessons learned from that mission. Ranger 5 missed. I would point out that there's also probably a lot of lessons learned from that mission too. When things go wrong, one of the fantastic things about being experimental is that you learn at least as much when the experiment fails as when it succeeds. Ranger 6, it impacted, but the cameras failed, so they got telemetry of the mission, but they hadn't got any pictures. Ranger 7 was a success, Ranger 8 was a success, and Ranger 9 was a success. So your NASA, with essentially an unlimited budget. This is the Cold War era. They are battling the Russians in terms of the space race, and so they've got an open checkbook to be able to do this. They've got access to some of the finest minds in the world, finest engineering minds in the world to solve these problems. Where do you start? Well, you don't start by drawing a Gantt chart. You don't start by predicting that Fred is going to be working on this particular part of the system on Tuesday in 1968. That's not how it works. You lay out a series of experiments and then you adapt based on what you learn from those experiments. That's how you do real engineering. That's how real design engineering happens. I want to reinforce that point a little bit. Here's a picture. Let's carry out an experiment. So there's a picture here with 2 orange dots surrounded by blue dots. Which dot is bigger? Make your decision. I can't see you putting your hands up, but make your decision. Is the dot on the left bigger? Is the dot on the right bigger? Or are they both the same? If you guessed that they're both the same, you've probably seen it before. They are indeed both the same. This is an optical illusion, and here's my experiment. I'm going to carry out my experiment. I'm going to measure the dots, and they are both identical. They don't look like it, but they are. Here's another one of those, just to reinforce the point. Hands up if you think that the line on the left is longer. Hands up if you think that the line on the right is longer. Hands up if you think that they're both the same. If you've seen this before, you probably guessed that they're both the same, but they're not. They're not both the same because I cheated. I made the line on the right longer. And I did that to reinforce the point that guessing isn't good enough. It's not good enough to guess about these things. We have to measure. We have to carry out the experiment. That's really what we're talking about here. The last in my list of 5 things is being empirical, based on, concerned with, or verifiable by observation or experience rather than theory or pure logic. Click. Being empirical means that we can make evidence-based and data-driven decisions. We can start to disambiguate mythology and guesswork from fact and truth. We can do research rather than guesswork, and we can start, if we're careful, to applying a little bit of science to the way in which we learn and improve things. We can never be certain of success. Progress only comes when we risk failure. We learn the most when reality does not match our predictions. If we just carry out an experiment and this experiment fulfills our prediction, then that's nice for our egos, but it's telling us less than if the experiment fails. One of the key ideas that kind of influenced 20th century science was the idea of falsifiability. We'd like ideas that we can disprove because it's very, very hard to prove ideas, and it's too easy to make a mistake of carrying out an experiment that's biased because you want a certain outcome. Disproving things is a more powerful approach. You can think of automated tests like that. Automated tests don't never prove that our software is good. But if one automated test fails, it proves that our software is not good enough. So falsifiability is a nice idea. Production is always going to surprise us. However diligent we are, however thorough we are, there's always going to be stuff that we didn't think of or we didn't predict. It's just the nature of the world. And it probably should. If we are not taking the risk that we might make a mistake, we're probably not really doing anything of any additional value. We're working within too tighter constraints. So we should be taking risks. Amazon boss Jeff Bezos says that if the level of risk that you take doesn't scale with the size of your organization, you're not doing it right. Amazon actively track the success or failure of the experiments that they carry out in production, and they carry out hundreds and thousands of experiments all of the time. And if 50% of their experiments are not failing, they up the level of risk that they take in the experiments, because that's how you learn. All of our design choices, all of our coding efforts, all of our tests, all of our documentation, all of our theories, all of our ideas about our software are really only our best theory to explain things so far. And our job, if we're to take it seriously as engineers, is to continuously review and refine our theories of things so far and improve them. If our tests are returning results in 5 minutes, can we make them return results in 4 minutes? If our product is the world-leading product, can we come up with a better product? All of those things are kind of, what we're talking about here. So, continuous delivery as an engineering discipline. The reason why I started talking about engineering was really after Jez and I wrote our continuous delivery book. I started thinking that the reason why it worked was because it applies many of these kind of engineering principles. We have short feedback cycles, test-driven development as a mechanism to drive better design, automation, hypothesis-driven decision-making, tests as a falsification mechanism. All of these ideas are fundamental to continuous delivery. And we've got the feedback loops that I talked about earlier. What we're really talking about here, though, is this. And I'm sure that people with a technical background will recognize this. This is the scientific method. We're going to make an observation of something. We're going to propose a theory to explain what it is that we observe. From that theory, we're going to make a prediction, and then we're going to carry out an experiment to validate or falsify that prediction. And then we're going to refine our observations and go around this loop. This is humanity's best problem-solving technique. If we want to become genuinely experts at problem-solving, we need to adopt this and take it to our heart. We need to apply this kind of thinking and become engineers rather than software developers in that sense. Often when we talk in our discipline, we talk by analogy. I've heard software development likened to making films or baking cakes at various times. And analogies are nice. I like analogies, but I'm not talking about analogy here. I'm not saying let's be like engineers. That's not my point. My point is let's be engineers. Let's start applying scientific principles to solving problems in software. That's my talk. Thank you very much indeed.
Hi, Dave. Okay, that was really a nice talk, basically, and it has maybe created lots of thoughts around us on that craftsmanship and software engineering, continuous delivery, overall things. So here is a chance, everyone. If you have any questions around this area or anything that you want to talk to Dave, please feel free to just write down in the questions. I will read it out and okay, I'm getting one. So we have a couple of more minutes, so I will just utilize that, Dave. So yeah. There is a question called, and I will just read it out for you. Why Scrum is not a good software process, as it will lead to lean process, iterative. Why we differentiate engineering as per nature or scalability applied to it, as engineering application is applied with respect to work to be done for that moment. Are you able to?
I'm sorry.
Also, if you can click on that. So you can just go ahead with the first one, like why is not a good software process, as it will lead to a lean process iterative.
So I wasn't saying that Scrum wasn't a good software process. I'm saying Scrum doesn't say anything about software. It's useful. It's applicable to software. It's effective in working with software, but it's not enough to be an engineering process. It doesn't say enough about the technicalities of software development for it to count as an engineering process. You can do very good Scrum, be very effective, and have very poor engineering. I think that when you ally Scrum with strong engineering, you get very good results. So I'm not denigrating Scrum. I'm just saying that's not its job. That's not the problem it's trying to solve.
Yeah, and another part of question was why we differentiate engineering as per nature or scalability applied to it, because so what he's saying that engineering, why we are differentiating engineering as per nature or scalability.
Sure.
Because
I would say that engineering is the difference between our modern high-tech civilization and what went before. So human beings have existed on our planet for somewhere between 200 and 300,000 years. And it's only 10,000 years ago that we got agriculture. It's only about 8,000 years ago, maybe not even that, but maybe 6,000 years ago that we got wheels. Everything that we recognize about our culture, nearly all of the advances stem from about 300 or 400 years ago when the Enlightenment started, and we started applying what we now think of as scientific principles to solving problems. Before that, we didn't do that. Before that, the way that we solved problems was mostly that we went with the opinion of the most important people. And engineering and science is about, not treating, it is about not trusting experts. It's about using evidence. It's about carrying out experiments. It's about validating our guesses. And that simple step, that simple ability to evaluate our ideas is what enabled our high-tech civilization. I think if you look wherever you're sat right now, if you look around you, everything that you see is probably the outcome of that kind of thinking. Certainly the computers in front of us, but even things like the chairs or the carpets or the wall coverings are probably have engineering thinking behind them somewhere. So I think engineering is one of humanity's, strongest tools for solving problems. And on the whole, it's not the way that most software is written. And I think it should be.
Okay. So the another question is, what would you recommend for data science project development? Scrum, Lean, Agile, or Kanban?
So I don't think any of them completely solve the problem. I think that the closest to my heart is kind of Lean process, probably organized around Kanban to some degree, but also with a little bit of kind of Scrum thinking in terms of breaking it down into iterations. And I know that's not a very clear answer. If you want to know more about what I'm talking about, try and head over to my YouTube channel because I talk about some of this kind of stuff. But the idea is that so Lean enough feels a little bit like it's fantastic. It's the most efficient way of doing things. The trouble is that from a human point of view, it gets a bit wearing over time. There's not enough human cycles in it. Scrum adds a more natural kind of human cycle, and so you can come to be a bit excited at the start of a sprint, and you can have some cake with your friends in the kickoff meeting, and then you have a retrospective at the end and feedback and all those kind of good things. So I think layering that human cycle on top of the most efficient approach, which is kind of Lean and Kanban, is the most effective way. What I've just described is kind of part of what I think of, the ideas that underpin an ability to continuously deliver. So continuous delivery, I think, is layered on top of that kind of thinking.
Okay, so the next question is on the continuous delivery side. So majority is not able to adopt continuous delivery against continuous deployment. What people need to do different to adopt continuous delivery?
The simple description of continuous delivery that I like is we're working to ensure that our software is releasable all the time. We're going to maintain our software in a releasable state all of the time. But that doesn't necessarily mean that we can or should release it. There are some organizations, so continuous delivery is working so our software is always releasable. Continuous deployment is if all of the automation says it's releasable, push it into production on an automated basis. That's fantastic for certain kind of businesses. It means Amazon can do things like release change into production once every 11.2 seconds, and they can learn incredibly quickly. Continuous delivery is really, if we're working in a way to keep our software in a releasable state, continuous delivery gives us great insight into the quality of our work. Releasing frequently gives us great insight into whether we're delivering the right things into the hands of users. And so that's a different opportunity to learn. There are some businesses where continuous deployment's ideal, but there are others where it would be inappropriate. You know, if you're Tesla, releasing changes into production while I'm driving down the road, I'd rather get the change when my car was in the garage. That kind of thing. So I think when you deploy is a business decision, and it varies depending on the nature of the problem.
Great. Okay, I guess we have one more question, but at the same time, I would like to tell everyone that we are going to have our next session just 5 minutes later. So I will just read it out, this question once, and we will get that here from Dave, and we will jump to that another session from Paul, right? So the last question is, do you think that we need to run lean on most of the agile projects or programs now? Many agile transformations are complicating the system instead of simplifying it.
My thinking is yes. I think so. My elevator pitch for lean is really about maximizing the output for the minimum input. We're trying to get the maximum out for the least amount of work by removing waste. So I think we should always be doing that, because really what all that is just focusing on efficiency. And so applying that kind of thinking, I'm a strong believer in agile principles. I'm not setting up one against the other. I think that lean and agile are both the same kind of discipline. The detail of where you have meetings, I don't care about very much. The fundamental is inspect and adapt and do it efficiently. And so those are kind of the principles that I build my approach on. Okay.
Thanks, Dave. And I would really like to thank you for getting time and coming to this conference. I believe that all the audience really get enlightened with your thoughts, and they were able to get some questions being answered as well. So thanks for your time. Thanks for joining this TAG conference. And so for the and for all the participants, our next talk is going to be aligned with Paul, and we have to get into that particular session. So I'm going to stop this session now here, so streaming will be getting stopped for you guys. Okay. Thanks once again, Dave, for your time.
Thank you. Thanks, everybody.